Hey, greetings and welcome, friends. We're talking about permutations with repetition and circular permutations. And as you can see, I've already participated in repetition by saying permutations at both the beginning and end of this title. Although I summarized it, abbreviated it, that's the word. Just perms and combos, that's what I'm talking about. So today, let's consider this example. That was a gross box. There we go, that's a little better. Let's consider how many ways can we arrange, arrange the letters in the word, let's say book. And I'll write it all lowercase. Ah, man, that was like a question mark that became a 3 all of a sudden. So, how many ways can we arrange the letters in the word book? So let's see, I could have B-O-O-K, I could have B-O-K-O, I could have B-K-O-O, right? Okay. Oh wait, I also could have B-O-O-K, right? Where I switched just those guys. Look at that little smiley face right there, right? But then I realized, well, those are kind of the same, aren't they? Right? Like for instance, if I also wrote Boko, where I switched these up, well, those are kind of the same too. I don't want to count those as two separate words. Like if I was trying to play Scrabble or something and I was just trying to find out how many possible letter combinations there were with the letters that I had, I would kind of consider those the same, right? Because I can't really tell the difference between one O and the other O. So the question is, how many extra O's do I got? How many extra O's do we have? Well, first of all, let's consider how many ways can I arrange 4 letters? Yeah, that would just be 4 factorial ways, right? And since I've got 2 O's that could switch position at any time, how many ways can I arrange 2 letters? 2 factorial. So if I just said 4 factorial was the answer here and said 24 combinations, well, I would have been including this and this, and I don't want to count that. So I actually have 2 factorial ways more than I want. So I'm going to actually divide 4 factorial by 2 factorial, the number of repetitions that I had, and I would have 4 times 3 times 2 factorial over 2 factorial. And those could cancel out, swing, swing, and I get 12. Aha. Actually, I wonder if we could find all 12. Yeah, sure, let's do it. So there's 3 that start with the letter B. Did I get all the ones that start with the letter B? I think so. Let's start with one with O. O-B-O-K. O-B-O-K. O-B-K-O. Then I could have O-K-B-O. Okay, Bo. Let's see. I could have O-Cob. Let's see. Am I missing one here? No, I think I got that one there. Let's see. I've got 7 so far. Let's do one that starts with K. So how about Koob, Kobo, Kebu. If I switch those, that's the same, right? So that doesn't count. Let's see, what else do I have to consider? Guys, I feel like I'm short. I need 2 more. Do I have all the ones that start with B and K? I feel like... Yeah, if I had 1 more in each of these, right? But I guess the 1 more was... Well, I don't know, guys. Now I can't find the other 2. This is awkward. Well, 6, that's 10. There's definitely 2 more though. What are they? Let's see. And you see how I tried a systematic approach where I was like, let's do all the ones that start with this letter, all the ones that start with that letter, right? O-B-O-K, O-B-K-O. Oh, wait, aha. Double O, O-O-B-K, and O-O-K-B. Aha, I'm glad we found it. I was worried there for a minute. So notice I do in fact have 12 unique combinations. There we go. Wonderful, wonderful, wonderful. So it turns out permutations with repetitions, I'll just abbreviate as perms with reps. Yeah, I don't know. Yeah, I don't know. So let's see. If the number of permutations of, let's see, if I have n objects, and let's say p are alike, and q are alike, then the number of permutations is the following, where it would just be n factorial, the total number of arrangements, and then I would just divide by p factorial and q factorial. All right, so if I had like 2, right, like in the case of the previous example, when I had 2 O's, right, I just divided by 2 factorial. But let's say I also had like 3 of another letter, then I'd also divide by 3 factorial, right? So the classic example is Mississippi, and having you figure out how many. Let's just do it. Yeah, let's do it. Why not?
So there's only one like repeated thing.
Yep, just one denominator. And if you have 7 repeated, like 7 unique repetitions, then you'd have 7 things in the denominator. So yeah, you could expand this to, right, so I could also have like r factorial and s factorial, right? However many things you need in the denominator is what you would do. So arrangements of Mississippi. Of M-I-S-S-I-S-S-I-P-P-I. Aha. So, how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 factorial over, let's see, how many M's are there? There's just 1. How many I's are there? There's 4. Yeah, so 4 factorial. How many S's? There's 4. And then 2 of the P's. All right. So this would be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. And I'll leave one of the 4 factorials in factorial form. And then the other one is 4 times 3 times 2, and then the times 2. Bam. So let's do some canceling. You could have also just typed this into a calculator, but I saw some nice canceling potential here.
So you can't add factorials on the bottom? Is that can't be like
if there was some problem where they told us to, but oftentimes you have the product of possible outcomes is often what we do. Let's see, 4 factorials cancel out, 3 and 2 is 6, and then 4 and 2 is 8. Looks like that would work. So this is equal to 11 times 10 times 9 times 7 times 5, if we've got them all. So that is 34650. Aha, not bad, right? So that's the idea of permutations with repetitions. Now consider the following. Consider the following. Different concept. How many ways can, let's say, 4 people sit at a circular table? Boy. So if I've got a table, right? I could have person 1 here, person 2 there, person 3 here, person 4 there. So that's 4 people being arranged, right? So that's kind of like a 4 factorial, right? I'm arranging 4 people. Or at least if they were sitting in a line, right, it would be 4 factorial ways for that to happen. However, consider the fact that this arrangement is really also the same as this. Right? How were those different? Yeah, it's just rotation, right, 90 degrees to the right. So I would consider that the same. And then what's another arrangement that would be the same? Yeah, I could have 1 on the bottom, 1, 2, 3, 4. And I also could have had 1 on the left, 1, 2, 3, 4. So I consider all of those the same arrangement. So there's 4 extra rotations that I have to consider that I need to get rid of. But it's not 4 factorial rotations I have to get rid of, just 4 rotations. So I'm going to divide by 4. So that would be 4 times 3 times 2 times 1 over 4. And the 4's cancel out. And I would get 6. 6 ways for 4 people to sit at a round table. So we could actually, with 4 students right here and a round table over there, we could try this as a lab experiment and write a lab report about it, I suppose. But that doesn't sound like that much fun. So we won't. Notice, what is another way I could have written this? Yeah, that's the same as 3 factorial, right? Which is 6, right? So it turns out for circular permutations, circular perms, if I have n objects arranged in a circle, the number of permutations is the following. And there's actually 2 ways to think about this. I could think about it as n factorial divided by n is one way. Or I could have just thought of it as, well, actually, how would you describe this 3 factorial compared to my original 4 people? It's 1 less factorial, right? So I could write this as n minus 1 in parentheses factorial is the other way you could perceive this. And those both give you the same thing, just because the way that cancels out, it works out identically. All right. Now, one last type of problem, which is circular but also has an additional concept, is what if I have, how many ways can I arrange some beads on a bracelet? Let's say I've got 6 beads on a bracelet. All right, and we'll assume that this bracelet has no clasp, it's indistinguishable, right? There's no knot in it, all right? So I'll just say with no clasp. So you cannot determine what order, right, where a starting point is. So if I have a bracelet with 6 unique beads, right, 1, 2, 3, 4, 5, 6. Now, in the case of the bracelet that we couldn't have done with the table, all right, now, like the table, we could rotate this and have 6 rotations that are similar, but I also could do this, and I want you to consider how these are similar / different. Yeah, I can flip a bracelet over, but I can't flip a table over and make people sit at it. Well, if I'm a nice person, I wouldn't make them do that. That's just weird. So, and how many types of flips are there, do you think? If I flip it over again, what happens? Well, it would bring me back to the start, right? Like 2 flips is, well, if I flip it, yeah, if I flip it like over this line instead of this line, you're saying? Well, then it's actually the same thing, but a rotation arrangement of it. So it turns out in this situation, I could calculate this by doing 6 factorial over 6 to deal with the rotations, but then I also would have to divide by 2, all right, or multiply my denominator by 2 to account for the flips. All right, so that's what this 2 is, the flip, and then this is the rotations. Right? Because I want to eliminate those duplicate answers where I can't tell the difference, right? Like I wouldn't know the difference. Like it's the same bracelet, right? Like you can be like, ah, it's a different one. Nope, I can't tell. So this is going to be, well, 5 factorial up top. Oh, how did I switch colors? So let's see, that would be 5 times 4 times 3 times 2 over, and this is just 2, not 2 factorial. I canceled out the 6 with the 6. And so this would cancel as well. So 20 times 3, so that's 60 possible bracelet arrangements. So I guess that's my one additional concept is flippable.
How would canceling out the 6 with the 6
Well, 6 factorial, it would have just looked like this.
Oh, yes.
Yep. So 6 factorial over 6 is the same as 5 factorial. So for flippable permutations, I'll just say divide by 2. Okay? And actually, ooh, maybe I've got one more type of question that might be worth considering. Yeah, we've got time. I should do it. What if I have this example? I guess this doesn't necessarily fit in this category, but you would be tempted to fit it in this category. All right? How many ways with the same bracelet? Let's see, 6 beads, bracelet with clasp. How many ways could I arrange that? And what I want to point out is that if it has this clasp, all right, I could have 1, 2, 3, 4, 5, 6. However, I could have just, when I open that bracelet, 1, 2, 3, 4, 5, 6, it would look like that. So it turns out because there was a unique point that I could fix the location at, it's no longer behaving in a circular way, and this is actually now just a linear relationship. So this one would actually just be straight up permutation 6, 6, or 6 factorial. Because I don't have the rotations or flips to consider, because I was able to re-perceive this as a linear relationship, and that's what 720, I believe, is what we end up getting there. So, so that's the idea of kind of eliminating our repetitions or rotations or reflections, similar to the video that we saw earlier about the tic-tac-toe example. All right, well, thanks for watching, friends, and have a great day. Bye-bye.